Hello, I'm Sam Albert, and I want to begin by acknowledging the lead author on this work, Dr. Jack Ridderhof, as well as our advisors, Dr. Tsiotras and Dr. Schaub. Today, I'm presenting our work, Linear Covariance Analysis of Entry and Aerocapture Trajectories in an Uncertain Atmosphere. To begin with some context setting, we often have some dynamical system of interest and want to understand its behavior in response to relevant uncertainties. A way this is commonly done is modeling that uncertainty and then using random sampling techniques, Monte Carlo analysis, for example, to generate some number of trials, some number of dispersed outputs, and then estimating the statistics of interest, the final state, the delta V, for example, from those random samples. An alternative approach that we'll focus on today is take that model of uncertainty. We'll generate a simpler model that we can then use in a linearization of the dynamics that allow us to propagate the state and its covariance together to directly estimate the covariance over time and other statistics of interest like delta V, no random sampling required. One tool that we can use to do this is a Karhunen-Loève expansion. So begin with a Gaussian random field psi. It has some mean function and some covariance function. And we can visualize this here where Z is the independent variable. And each of these lines is a single random instantiation of that random field. It becomes a continuous random function. We can also imagine a slice at any value of Z, and we would then have a probability density function for any value of that independent variable. So this is an infinite dimensional representation of this uncertainty. So we can take that covariance function and solve the eigenproblem to get the eigenvalues and eigenfunctions of that covariance function. And then we will form an orthogonal decomposition of this random field. And we will choose the basis such that it is minimum mean square error for any finite number of terms. And this is known as a Karhunen-Loève expansion. So you can see this is the exact representation where we have an infinite number of terms. We have the eigenfunctions appearing here, and the randomness comes in through these variables W sub I, which are independent and identically distributed variables with a variance equal to the eigenvalues of that covariance function. And then here, again, we just truncate that summation to obtain this finite dimensional parametric representation of uncertainty. So as a quick example, the math on the left is just there for completeness, but we'll plot Brownian motion and then apply the Karhunen-Loève expansion, which we can do by first analytically, in this case, finding the eigenfunctions of that covariance function, and then seeing how this expansion behaves as we increase the number of terms in the approximation. So unsurprisingly, 1 doesn't look very good, but with 10 terms already, it's beginning to look like something, and then by 100 terms, we have behavior that is very similar to what we would have for the true Brownian motion. So now we'll do essentially the same thing, but for density variability as a function of altitude. For our truth model here, we're using Mars-Gram, plotting a couple of sample density profiles, as well as shading the plus or minus 2 sigma bounds. So we can take the sample covariance matrix, use that as an approximation of the covariance function of the true random field, and then take the eigenvectors of that matrix, which are shown here on the left. And that results in an expansion as shown, where here we're using a number of 50 terms. So the bottom row here is from 0 to 40 kilometers altitude, and you can see that this approximation performs very well there. And then showing all the way up to 125 kilometers altitude, the approximation is worse here where the altitudes are high and the densities are low, because although we are showing percent density variation here, the expansion itself is on the actual value of density. And in short, this turns out to be okay because most of the dynamic pressure occurs in this region anyway, and our predictions still perform quite well. Although you could do this expansion differently if you had different requirements. So we can incorporate this into a linear covariance analysis, which I won't be able to spend much time on in this brief presentation, but suffice to say here that we have some sensitivity matrix S, which we can compute by propagating this ordinary differential equation shown here. And looking at this form, we have 2 terms where the first term looks familiar. This is how you would compute the state transition matrix for a deterministic system. And then the second term incorporates the effect of the random field variations. So we have this chain rule partial derivatives The first partials are just the dynamics with respect to density, which is in this case our random field. So that just falls out of the dynamics. And then the second component is the partial of that expansion with respect to these random variables. So that just becomes these eigenvectors. And so this is how we can compute that sensitivity matrix. And that in turn allows us to compute the state covariance matrix by also including this covariance matrix of the parameter vector from the expansion, which, if you will recall, is simply a diagonal matrix where the values are the eigenvalues from that sample covariance matrix that we formed. So to briefly summarize here, we've treated the variability of density using a Karhunen-Loève expansion to obtain this finite dimensional representation. And using those uncertain parameters from that expansion, we can incorporate that relatively high fidelity model of density variability into a linear covariance analysis, which we'll now use for a couple of different implementations. The first one here is a guided entry scenario at Mars. And we're doing all of this for the closed loop system. In this case, we're implementing Apollo guidance. And so this is a linear feedback law. And what we're showing here are some different states and the control. And the black lines are the plus or minus 3 sigma bounds estimated by the linear covariance approximation using a 50-term Karhunen-Loève expansion. And then the dashed lines are the same value, but from the 5,000 trial Monte Carlo analysis, where we're using MarsGram directly. And you can see that they match nearly exactly. And this is great. It allows us to do a much faster prediction of the evolution of covariance than you can do by a random sampling technique. We applied it to Aerocapture as well. In this case, the control comes from adapting Apollo guidance for Aerocapture, also known as terminal point control. And again, the linear covariance approximation matches very well with the Monte Carlo data. And we've gone one step further in this case, and we're showing histograms of a few quantities of interest, specifically altitude at apoapsis, velocity at apoapsis, and delta V for periapsis rays. And then we are also generating a Gaussian distribution from the linear covariance approximation. And you can see that that too matches quite well with the Monte Carlo results. This is great because we can then directly estimate a quantity like, for example, the 99th percentile value of altitude at apoapsis, and expect that to be a value very similar to what you'd get doing Monte Carlo analysis. And so to recap here, we've shown that you can do this analysis of the way that uncertainty affects entry trajectories by using this Karhunen-Loève expansion for density variability. And we compare that to this Monte Carlo approach. And I will close with one caveat, which is that, of course, outside of all of this exists the real world, reality, and there's always some modeling error. MarsGram is not a forecast model per se, and it's not the actual Martian atmosphere. And so there's always some error in this approximation. And to be sure, that affects either of these approaches. Any kind of guidance that you tune will be subject to this. But we're incorporating even more information from the model here by explicitly treating the system as stochastic with information that we got from MarsGram. So the approach that we've shown here is potentially more susceptible to this kind of modeling error than an approach that treats the system as deterministic and is then tuned using this information. So I think that's a point worth mentioning. But that being said, we've shown that the approach here matches very well with something like Monte Carlo, but because it runs faster, it could be incorporated into onboard guidance. It could also, for example, be used to simultaneously optimize the reference trajectory and feedback control law for guidance on the ground. With that, I look forward to the in-person session. If you have any questions, please feel free to email Jack or myself at the emails listed here. Thanks.